C1 e to the t plus C2 e to the 2t. So C1 e to the 0, C2 e to the 0 equals 1. So C1 plus C2 equals 1. And we also know, first we should find the derivative, right? So x prime of t is C1 e to the t plus 2 C2 e to the 2t. Okay, and we're told that the value of the derivative at 0 is 2. So again, if we substitute 0, this is 1 and this is 1. So C1 plus 2C2 equals 2. Okay, so we have this system to solve. So C1 plus C2 equals 1. C1 plus 2C2 is equal to 2. So there are several techniques that you could use to solve this. This one's it's pretty easy to use elimination, right? You just have to subtract one from the other. Or you could solve for one of them, like solve for C1 by subtracting C2 and substitute it into the second equation. Or, you know, if you want, I would suspect that most of your calculators can handle these systems. Now you need to be careful with that, because if you're going to use your calculator to solve the system, because sometimes the constants are irrational. So your calculator would only give you an estimation. So let me use elimination. So if I multiply the second equation by -1, add them, that's minus C2 equals -1, C2 equals 1. What do you do with this? Now that I know one of the values, I substitute into either one of the equations. C1 plus 1 equals 1. So C1 equals 0. Okay, now don't forget to take these and tell me what the solution is to this initial value problem. This gives us the coefficients, or the values for the parameter. So the IVP is x of t. C1 is equal to 0, right? So C2 equals 1, 2t. Got it?
Oh, that's the idea. Okay.
Any questions? All right, so you can think of, mathematically think of this as giving us enough information in order to determine the parameters. If you want to think of this in practice, I mean, what is a differential equation telling us about some real-world situation? What does a derivative tell us, or what does it measure?
It's how it's changing.
Its rates of change, right? So the differential equation is giving us some sort of relationship of rates of change, right? The most common rate of change is speed. Okay, so let's think of the derivative as representing something about speed. So, if we have information about speed, but we're trying to recover the function itself instead of its derivative, right? What's the quantity that we would be interested in? If dx dt is speed, x is displacement, right? So the solution is going to tell us something about displacement, right? So let me give you a simple example to make this more clear. So let's say I tell you I'm traveling 70 miles an hour down Highway 70 headed towards Kansas City. After 1 hour, which mile marker am I at?
That's going to be.
No, it's
No.
It could be.
Where'd you start?
There's missing information, right? I need to tell you which mile marker I began at. You see what I mean? So once I tell you which mile marker I've begun at, then you can tell me which mile marker I end at, right? What is the information about the mile marker that I began at? That's the initial condition, right? So if I tell you something about speed, and we ultimately want to use that to determine something about displacement or position, then we need to know where we began in addition to the speed that we're traveling. Does that make sense? So that's the rationale behind why we need these initial conditions. How many of you have had physics? Most of you, so do you know the formula for position under constant acceleration.
1/2 AT squared.
Yeah, that's the one. Good to know. So if you want to determine the position, so this is one-dimensional motion under constant acceleration. The position is, say,
1/2 AT squared.
1/2 AT squared. Yeah.
Plus BT.
Plus B0T, right? Initial velocity. Plus,
X naught.
yeah, initial position, right? Have you seen this before? Do you know where this formula comes from?
I'm sure I've done the integration and differentiation before.
Yeah, I mean, basically everything in physics is a second order differential equation, or second order initial value problem. Like, you know, anytime you're talking about force, right? Force is mass times acceleration. What is acceleration? What's in terms of
Acceleration due
derivatives?
to gravity.
It's the second derivative position, right? So anytime you're using Newton's second law, it's basically a second order differential equation. So let's try to do this from scratch. So, so the information says the particle's accelerating constant a, so you should understand a is the acceleration, it's some constant. And let's call the position when time is equal to 0, x naught, and the velocity when time is equal to 0, v naught. So let's create an initial value problem and determine the solution. So how can we take that information? So first of all, we need to create a differential equation, and we need two initial values. You with me on the third page?
You just have an initial velocity be 0.
We don't get to choose the initial velocity. We're told that it's something, and we're going to call it v sub 0. So determine the position. So let's call the position x of t. Right, so let's call the position as a function of time. This. Anyone? So I need a differential equation and initial values on this information. Acceleration is constant, a meters per second squared. At t equals 0, its position was x sub 0. At t equals 0, the velocity was v sub 0.
Start with that formula. 1/2 AT.
We're going to derive this formula.
Well, velocity times time would be the first derivative.
So are we taking,
Velocity times time is the first derivative.
are we taking the first derivative of that?
This
So
is
we're gonna be
this
at
is going to
18.
be the answer. So ignore this. I'm just reminding you what the formula is. That's going to be the answer to all of this. What can you make of at t equals 0, its position was x sub 0?
So the position's x naught.
So what is position? X of t. What's the position when t equals 0? X of 0.
0?
So x of 0 is equal to what? X naught. Right? When t equals 0, the position is x of 0. Okay, I did the easy one. What about the velocity v sub 0? When t is equal to 0, the velocity is v sub 0. So if this represents position, I guess if you want to be technical, displacement, then this is velocity, right? This is. Okay. So what to make of at t equals 0, the velocity was v sub 0.
V sub 0 equals V naught.
Okay, so v sub 0 equals v naught. Alright, but what is v? We don't want to introduce another variable.
We
That's
should
fine.
be
Yeah,
velocity.
v sub 0, that's x prime of 0, right?
Yeah.
So x prime of 0 equals v sub 0. Okay, so these are the initial conditions. Anyone know what the differential equation is? Must come from the first half of the sentence. Particle is accelerating at a constant a meters per second squared.
So we start at A and integrate our way up.
Integrate what?
Acceleration.
What is the acceleration of this particle? X double prime. Right? Acceleration is the second derivative, and we're told that it's constant. Right? So that means what? That means that x double prime equals a. Are you with me? Right? So the acceleration in general is the second derivative, but in this case, we're told that that acceleration is constant. Okay? So how do we solve this equation?
We'll integrate A.
Well, we could integrate twice, but let's do it once at a time. Okay. So, right, so let's integrate once. It's a bit ambiguous. What variable are we integrating with respect to? T, right. The independent variable is t. So the integral of x double prime dt. Let me write it this way. d2x dt squared is equal to the integral of a dt. Okay, what is this? This is x prime, right? So let me write it as dx dt. Right? The integral of the second derivative is the first derivative. What is this integral of a dt?
AT.
Almost. Since a is constant, it's at plus c. With me?
Yes.
Okay, so we could rewrite this as x prime of t is equal to at plus c. Okay, and we're looking for x, right? So what should we do to find x?
Should we solve for C now, or do we keep
Oh,
integrating?
we can do that. I was going to solve for them later on. So we'll need to integrate again, right? That's going to introduce another constant, right? So let me label this as c sub 1. Okay, so to find x, we integrate with respect to t again. Okay, so the integral of the derivative is the function, so left-hand side is x of t. What is the integral of at?
1/2 AT squared.
1/2 at squared. Integral of c1,
C1T.
c1t. Okay, and then introduce another constant plus c2. Okay, so this is going to be the form of the position function regardless of the initial conditions, right? It's always going to be 1/2 at squared, and then the rest of this will depend on the initial conditions, right? So let's determine c1 and c2 by substituting, so you can probably guess what we're going to find. Let's substitute into the derivative first. So we're calling the value of the velocity Okay, so now we have values for the parameters, we substitute them to the general solution, we get so t equals half a t squared plus 0 t plus x is 0. The idea? Would you like to try the next one?